Okay, we have an interesting integral here today. This is a generalization based off a problem that I got from Caltech Math Meet where it was simpler. It was, I think K was just 4. Now here, the thing that's going to make it a little more complicated, yes, we want K greater than 0, but K doesn't have to be an integer now. I think a good starting point for it is actually looking at a graph. Hopefully I can post like a graph from Desmos or something. But let's just do a quick rough graph of what happens with the fractional part here. Assuming for a minute that K is going to be greater than 1, what happens with the fractional part is you get this kind of repeating action with the graph. So it's going to be like something, if like this is 1, it's just going to, for all these integer sections, it's just going to repeat over and over again like this. So in that other video, when we had it going from 0 to 4, we just took the 4 out front because it just repeats over and over again. So we just need to find like this area and then multiply it by as many times as this, and it repeats over and over again. The trouble with this is we don't know that K is an integer, right? So like if this is 3 and then it just stops right here, then we can't just multiply by a constant. We need to find this additional area right here. So the way we can do this is break it up into 2 pieces, because we can pick like some integer point here. Like this is going to be the floor of K, and then deal with this little piece separately. Because this piece, if the floor of K is always an integer, then this part's going to be easy. We break it up into 2 integrals. We calculate this one, knowing it's an integer, and then we calculate this little part. What we can do for this is we can start with the formula for the fraction part. If we have the fraction part of x, we have this formula that's the same thing as x minus the floor function of x. If you're not too familiar, I don't want to use the same number I used right there. Let's use like something like, let's do pi. Can we do pi? The fraction part of pi. So the fraction part of pi is going to be just pi minus the floor function of pi. But the floor of pi is just 3. So we end up with pi minus 3. I don't know if this is the best example, but we just want to think about pi right now as like 3.14 something. And then we're just left with this part, the 0.14, which in reality has an infinite number of digits that I only know like 4 of. But anyway, we want to use this formula, and we want to use this in this case on our K. If you just rearrange this, like x equals the fraction part of x plus the floor function of x. In our case, we're dealing with K, just a different variable. We can say that K is the same thing as the fraction part of K plus the floor function of K. So just to save some writing, let me take this thing right here and plug it right back in for K in our problem and make that the upper bound. But then doing it like that, it gives me a way to split this in 2 integrals. Not really, just doing what we usually do. If you have, it's nothing, it might look kind of complicated, but if you have an integral from 0 to 4, you could split it like this, right? So I'm just going to do the same kind of thing with this more confusing expression. How I'll do it is I'll split it. The first part's going to go from 0 to the floor of K. That way we guarantee it stops at this integer point, so we have something that's going to be easy to deal with. And then for the second one, we'll just continue from this point. We can't have any breaks in it because then we're changing the problem. And then we need to go all the way to this crazy expression here, which I'm messing up. And now that we have it broken up like this, I want to go back to this formula and use it on x. And this is what we did in the last problem. This is basically the method we used in that last problem from Caltech Math Meet. We broke it up this way because it made it easier to deal with. So I'm going to do the same thing here on both these and just plug this in for this. And now at this point, this is where the graph comes in handy, because we know we have this property that it's just repeating, especially here. So now this is an integer. Like I said before, just repeating, so this can come out front as a constant. So we can bring this right here and then change this to 1 just because all we need to do is integrate it from 0 to 1, and then everything else just repeats. And then on this second integral, we can do something kind of similar, because now even though it's a little, even though my graph isn't very good and it's kind of confusing, this piece right here is the same thing as this piece right here, and this piece right here, and this piece right here. It doesn't matter which of these intervals we evaluate it, because it's going to be the same area for any of these. So I can just choose it to be this one. And the way I can do that is set this bound to 0. We set this to the fraction part. That's going to be this right here. This is the fractional part of k, is the same thing as that. And we don't have to bring anything in front. We can just, it's just equal to it. So we can just update our bounds like this. But that's going to do a lot of the work for us, because on this first one from 0 to 1, the floor function rounds us down. So in this region from 0 to 1, everything gets rounded down to 0. So that goes to 0, and that's good. Same thing over here with the fraction part. The fraction part of k can't be, it can never be 1. It's always going to be between 0 and 1. So what's going to happen? Same thing. This is going to get rounded down to 0, and we're just left with x. So this whole thing is going to get really simple, because we're integrating from 0 to 1 over here, and it just becomes x to the n, which is power rule. And we need a dx technically to do this. And then over here, just different bounds, but again, this is going to be x to the n. So we'll go ahead and do it with power rule. First we have floor of k, x to the n plus 1 over n plus 1. And then here, actually, okay, we need to evaluate from 0 to 1. And then over here, it's just going to be same thing, x to the n plus 1 over n plus 1. Okay, now we go ahead and evaluate. Notice that 0 is going to 0 everything out when you plug in here. Over here, you plug in 1, that's just, the exponent doesn't matter, so it's just going to be a 1 right there. So what we're going to get is going to be floor of k over n plus 1. And then here, just plug that in. That's just going to be whatever it is. So that's just going to go right in there. So it's just going to be the fraction part of k to the n plus 1 over n plus 1. And we have the common denominator. So what I'll do is just put that together. For my final solution on it, we just get floor of k plus fraction part of k to the n plus 1 over n plus 1, and that's it. And then you might be wondering about different cases, like that problem we did in that other video. We were going from 0 to 4, so we had an integer, and it was pretty simple. What happens is, though, if k is an integer, this right here becomes a 0, and so that part falls off. And then if k is an integer, then this is just k right here. The floor doesn't do anything. So your integer formula for k, maybe assuming still greater than 0, would just be k over n plus 1. And so this right here, nice simplification if you're just dealing with integers. All right, that's it for today. Thanks everyone for watching. Have a good day.